So welcome everyone. Today I will talk about the Wei-Norman method applied in the Anticommuting operators program. The method was described by Szymon some time ago, so I think maybe it's not quite it's not completely new. So let us begin with the general problem. We have the first order differential equation with some given initial conditions. And at the first sight, the solution seems to be obvious, given by this formula. But unfortunately, if M and K are matrices, or in general, if M from different moments of time do not commute, this formula is not true, but however, K is still an exponential function of an unknown function of the operator M. The exact form of this function was derived by Magnus in 1954. Magnus proved that if M was an element of the associative algebra over, for example, real or complex numbers, precisely over the field of characteristic 0, the solution K is the exponential function of a so-called Magnus series, where I decided to give on the slide the first 8 terms. As one can see, the first term is simply the integral of M, but the next terms depend on the values of M and the commutators between M of different moments of time. Obviously, if M is constant and do not change in time, then only the first term is non-zero, and the solution is given by the simple form.
Sorry, shouldn't you assume anything about completeness of this algebra?
No. There was nothing about the completeness. No.
At that moment, it is not an algebraic result in a sense, because as you see, you do not use any properties of commutators. It's simply expansion.
But you have
Magnus
infinite series,
used only
right?
the associativity.
How can we know it's converges?
It usually does not converge.
Yeah, so
I can only add that this formula was generalized and extended by the late Professor Plebański and myself.
Yes, exactly. I wanted to say that at that moment one should always involve.
And I wrote my PhD long time ago by applying this to
and what's interesting, I also wrote my PhD by applying that.
Did any one of you know that you are applying a Wei-Norman method?
No.
Yes. Yes, I did it. And in my case, in my PhD is even explicitly written.
There is a one person.
But this is still not Wei-Norman.
Who is honest about this?
But obviously at that moment there were many attempts, and this what was in the 2 papers by Mielnik and Plebański and Białowicki actually solved the problem to a large extent. Okay, so at least they gave the formulas which were applicable in PhDs.
Yes.
Well, actually, this is.
But is the fourth term also usable, or?
Yes.
Whereas it's explicitly known.
It's
exactly.
For simple matrices, probably it's even useful.
Yes, and moreover,
this this series is infinite.
Of course. Yes, of course.
But
For matrices it is convergent, okay?
Yeah.
And for mysterious reasons, this formula is a very magic formula which is used by all these which are involved in control theory and something like that, okay? So there is even a paper which was written 2 years ago, which is a review paper about Magnus form.
well, actually, the Magnus expansion is still not the Wei-Norman formula, but this is the first step to prove it. Because sometime after Magnus, Norman simplified his formula under some additional assumptions. At first, they assumed that the solution K is a curve in a Lie group denoted by G. So the derivative K is the element of a Lie algebra of the Lie group G, and also M is an element of the Lie algebra, where M is a linear superposition of basis vectors of the Lie algebra. The basis vectors are constant in time, but the coefficients can change. Then Wei-Norman proved that if K is written as described as an exponential function of a sum, it could be transformed. It could be transformed into the product of exponentials where the coefficients C and G are connected with each other by this matrix equation. Matrix A has been introduced by Wei-Norman by this formula, and some basic facts about this algorithm. At first, the Wei-Norman formula uses Lie groups and Lie algebras properties, especially the so-called adjoint action in a Lie group and a Lie algebra. And the commutators appear in this method by definition in this expression, because this symbol denoted the adjoint action in the Lie algebra, which is defined using the commutator between the elements xy and xj. Of course, they are both belong to the Lie algebra.
Pewno się baterię włączy, ja się dowiem, czy pani Magda ma baterię.
The question is if the commutators are necessary in this method. So let us begin with the derivative. If we describe the solution as the product of exponentials of basis vectors multiplied by some coefficients, then it's very easy to calculate the derivative. algebras properties, as I mentioned precisely. It's
The pointer is now in action.
precisely it's adjoint action in Lie group and Lie algebras. One can present the derivative of the solution in this form. That means it is possible to extract the solution multiplied by some function. It's of course the general function dependent of the coefficients and basis vectors. In general, it is unknown. In the case of Lie groups and Lie algebras, F equals this. And then the Wei-Norman formula consists in comparing this factor and the matrix M. And this is exactly this equation. So the question is whether such algorithm is possible in general, especially using not commutators, but in the case of anticommuting structures. And actually, two, I think, very natural ways come to mind. At first, one can use the operators as basis vectors that satisfy canonical anti-commutation relations, that means fermionic operators, and then use the whole Lie group and Lie algebras machinery, because also anti-commuting operators may generate the Lie algebra, or completely redefine this Wei-Norman method using the structure for which the anti-commutator is a natural operation. And both structures, especially useful in quantum mechanics, are Jordan algebras. So let us begin with the first part and consider the fermionic Schrödinger equation, which is very, as one can see, it's very similar to the equation presented on the first slide. And let us consider the simplest problem.
This old-fashioned little I from Schrödinger equation
Is somewhere.
is somewhere in H, or should I already forgot about I in Schrödinger equation?
Is somewhere.
Because then it changes the property of H,
That's true.
I believe. But I mean, of course,
If
it's
H belongs to
old-fashioned.
Lie algebra, then
It's old-fashioned. Or T maybe, or maybe
No,
Islamic.
it's missing. But the excuse is such that when you go to the algebras, then
Well, since I'm
mathematical Lie
I'm
algebra.
dramatically trying to cope with the beauty of this mathematics,
it's missing.
I would not even dare to assume that the I is
Now it's missing, but you see that that in a sense that you should put this I somewhere.
But you
I
see
think.
below even two eyes. So one is
actually three eyes.
yes.
So not two eyes. So it's
Now it's missing.
an odd number of eyes. So
Are
it's-
these plus and minus indices not supposed to be interchanged? That
Well,
Dimension
it's
conjugate.
my notation to, it's just my notation to simplified.
Okay, anyway, I
It does not mean that plus goes with plus and minus that could be plus and
is the
minus or
equation
plus and
operator,
minus.
and minus the annihilation.
Yes,
So
but then
this
it
is
so
the
then the
most
product
general
should be
form.
plus
It's
and
just
minus.
the general
No.
quadratic form.
No.
No?
Oh, I start with the
that's where the idea.
Yes, are we talking about the Hermitian operator H or not? The first
The
question.
hermicity is somehow
It's one
encoded
slide
in C's rather,
Yes.
rather than in A's.
Okay.
details are given one slide. On the next slide, this is the most general form. Of course, I'm really sorry I missed the I. But if we have the quadratic operator, it has the simplest Hamiltonian that has a physical sense. It must be rewritten as a linear operator
And where is time dependence now?
in
On the left side of
coefficients.
the missing
In the
eye,
coefficients.
of the missing eye.
Okay.
And Wei-Norman algorithm requires that this operator must be linear superpositions of basis vectors. So xk are basis vectors. And it could be done both for Dirac fermions and Majorana fermions. I found only one Hamiltonian for Majorana fermions describing the Kitaev model. And this is the Hamiltonian, the general quadratic Hamiltonian written in matrix form.
And now it's
as
obviously
one can
Hermitian.
see, they are Hermitian. And now, this is the most general form of the vector xk, but of course the canonical anticommutation relations and Pauli exclusion principle that results from them leave only 6 generally independent such operators non-zero, and maybe some facts that I think are very important. At first, the fermionic annihilation and creation operators and their linear superposition form the Lie algebra speed 2n when n is the number of possible modes, which is the covering of the special orthogonal algebra, but the vectors used in the Wei-Norman method do not form this algebra because they are not linear superposition. But we have the multiplied operators. But fortunately, they also form a Lie algebra after the, let's say, complexification with one additional vector. And I named this algebra as df.
I understand that the anti-commutation relations are standard for the operator A, just the delta function.
Yes, yes.
Can you go back to this first? Because this Hamiltonian does not conserve the number of particles.
Yes,
Right.
Yes.
So this is not two Dirac fermions. It is 0, 1, or 2. Inside. Yes? You
Yes.
have two levels,
Yeah,
and
well,
you have.
That
From
depends
zero to-
on the C's, whether that.
Yes, but in general, this Hamiltonian does not conserve the number.
Does
of
not.
particles.
In general, yes.
True, yeah. In general, yes.
Yes, I consider the most general problem.
But in the Kitaev
This-
model, it could.
Some properties of the algebra generated by basis vectors. At first is the simple Lie algebra and its dimension equals 7. Then basis vectors satisfy very simple.
But they're semi-simple.
Very simple commutation relations.
Something is wrong. The first line is the same commutator is either 0 or xij, so something is wrong.
What's the difference between the first commutator and the second?
It's wrong. Something is funny.
Because
There is 0
this
and
case and this case are different. For example, this is the
It's
commutator
either.
between
so it's
x1
either
and
or.
x2 and for example x1 and x3.
So for some I and j
Oh, yeah.
equation.
So this is,
Yes.
as far as is concerned, the structure of this commutation relations that an exact rather than exact form of them. So that means that some commute, some
commute and
and
So
some
this
don't.
order
As it is written,
Yes.
it's
is
misleading.
really
Definitely.
for unexperienced readers.
No, for
even for experience.
for a layman. Not.
This algebra is also a direct sum of two
So it's it's rather semi-simple than simple.
of
Okay,
two
that doesn't matter.
sub-algebras. And the first four vectors, that means the vectors that conserve the number of particles belong to the first subalgebra, and the vectors that do not conserve the number of particles belong to the second subalgebra. And the algebra DR2 satisfies the conditions for the Aldous theorem. That means that it is finite dimensional and over the real complex numbers, so it can be represented as an algebra of tail n times n matrices, when n is the dimension with elements belonging to the field K. The most natural way to obtain the matrix representation of this algebra is to use Jordan-Wigner transformation. And at first, for Dirac-Fermat, Jordan-Wigner transformation transforms commuting into
Jordan, so there is a question of Jordan because this is bad Jordan. This physicist Jordan. It's Jordan.
In the United States it's Jordan.
In the United States it's Jordan. Okay.
Jordan.
But this is Jordan.
Dobry Niemiec.
Pan Jordan.
Nie bardzo dobry.
Strasznie przepraszam. Ja bym chciał, a potem doszło do Bundestagu, ale po wojnie, ale ja bym tak był ostrożny.
And these algebras which will appear further, these are also Jordan algebras because these are the algebras which are somehow invented by him.
Ale to jest ten sam Jordan do reprezentacji Jordana.
Probably this is the most common way to transform commuting into anti-commuting operators using standard Pauli matrices. And if we use the transformation for the one-dimensional spin chain, the Fermi operators, that minus means annihilation operator and plus means creation operator, are given by this
So
formula. Where sigma plus minus is
I believe that for some people in this room, the question one-dimensional spin chain which can be transformed via this trick which is known since 20s may not be clear. What do you mean by the one-dimensional chain of those speeds? Why one dimension? There is no dimension. There are labels.
Yes, I think that this is misleading. This is, yes, I completely agree. There is no dimension in that.
And there is no one dimension.
There's
It's
no
a,
chain.
well, in some sense
There will be
it is.
unstable interaction.
Because the question is in the Hamiltonian.
Unstable interaction.
Because this transformation, these are A's which were sitting in H, and the H for the one for the spin chain has a particular structure.
For example,
So is this particular structure used or not? I mean,
Yes, but there will be an interaction. There will be a near stable interaction. I think.
well, the question that not any spin interaction in the chain can be transformed by this. I mean, the question is what kind of a chain is being used. I mean, the formula looks like this. There were operators A, which appear in the Hamiltonian. They were more or less, in a very funny way, written all known fermionic commutation relation. Now this A is written as another combination of a Pauli matrix
Yes.
with a mysterious word for the one-dimensional spin chain. I'm just asking, what does that mean?
In order to apply this definition,
What kind of a-
one must
You
order
have to order
the
them.
labels.
That's what I'm.
Yes.
Yeah.
I'm not asking you.
for example,
Jesus
I
Christ.
found in some articles the operators labeled by two indices.
Okay, so no, I think that the question, the answer is exactly as it was done. So this is simply some order in this, and this is,
That's the only thing that.
and this is the name.
That's the name.
Order sequence. You will call it chain.
In this representation,
Next.
basis
Years labor, next year's labor.
in this representation, the basis vectors are 4 times 4 matrices with the determinant 0 and the span subspace. This is the explicit Wei-Norman formula for this problem. And for example, if we apply this method for the BCS Hamiltonian, which is slightly easier.
Isn't that this is in a very funny way written what actually some people will call a Bogoliubov diagonalization of this
Yes.
Hamiltonian, or I will call a Valatin because it was done before Bogoliubov, and that of course
It
expresses.
will be about Bogoliubov transformation soon, as far as I understand.
Yeah. So all this complicated thing is actually Bogoliubov transformation for this one.
Yes and no.
Then I compared this method with the Bogoliubov transformation. So the BCS Hamiltonian written for using the basis vectors looks like this, and the exact solution of the Wei-Norman formula, that means the coefficients GI are given by this relatively simple equations, because for example, if we try to integrate this coefficient, we treat all those coefficients as constant parameters. That means the integration is trivial. I marked the coefficient G1 and G2 with red color, because only in these two cases the integration is non-trivial. This means the GI, well, the derivative of GI is also the function of G1. There exists a well-defined exponential map that transfers the elements from the Lie algebra to the elements of...
But this particular solution in terms of the things I mean in terms of this ease, in the physical Hamiltonian there are three energies, right? Of one level, the second level, and the exchange between them. And so this particular solution is somehow given in terms of this ease.
Yes.
And what is particular for that solution in terms of this ease? I mean, if it's a particular, it has a certain form, so does that correspond to a peculiar relation between the energies of levels and correlation? Or?
No, this is as far as I understand the general solution for arbitrary.
So
Can you show the previous transparency
The coefficients are arbitrary in the Hamiltonian.
in the Hamiltonian?
Yes, some coefficients are arbitrarily given. And
yeah, but the GIs are given in terms of ease.
Yes.
Okay, so this formula could have been written. So this is a general solution of this model. So there is nothing else than the Bogolubov solution for this. I mean, it cannot be anything else.
In the Bogolubov problem,
Yeah, but
there is no time-dependent
That's right.
Hamiltonian. It's quite
So
different.
these e's are time-dependent.
Yes.
Yes.
That's why K of t is the function of t.
So these are arbitrary time-dependent coefficients. right?
Yes.
Yes.
That's the difference.
it's precisely these coefficients
And
are
the difference
dependent.
is for two operators. This Bogolubov transformation.
Yeah, well, then I can use this Bogolubov solution for two.
These coefficients depend on the Hamiltonian. And as for the properties of the solution, K holds the algebra that is non-compact, not connected, and for some well-matched initial conditions, it
But
belongs to
basically, excuse me, I mean, I know I'm making fuss, but I'm trying to understand some physics. In this real model, the only sensible time-dependent can be in this E correlation, because the E1 and E2 cannot. I mean, these are the energy of levels. How they can depend on time?
It depends on the physical
That's
situation.
right. In these atomic physics problems, you can just very often change
okay.
the trap or something, and then you will change the levels. Of course.
Okay, so definitely
That's the answer.
okay.
Then let us try to generalize this problem to n particles. The method is exactly the same. That means the operators generate a Lie algebra. However, the dimension grows rapidly like n squared. And the basis fact that this expression for the basis vectors is always finite, and it could be either linear, given by this expression, or this can be written as a Taylor expansion that results from the commutation relations between the basis vectors. So if we have the matrix of coefficients, it seems to be relatively easy. That means it contains many linear elements, but unfortunately, if we want to obtain GI coefficients, the matrix A must be inverted. And if we invert it, the Wei-Norman equations for GI coefficients become very complicated. So
at this algebraic level, I don't see any justification for calling these Dirac fermions, because these are just
fermions.
creation annihilation operators.
These are just fermions.
Yes, but why Dirac fermions? It doesn't make sense. Dirac and Majorana become significant when you have a field which satisfies the evolution equation, but not at this level.
That was also true in relation to this Kitaev model, because this exchange was done such that the electric field is applied to this real physical model. It picks up the Majorana.
But what's the difference between AI for Dirac and for Majorana fermions?
It's nice word.
No, but what is the difference between when you have a collection of creation annihilation operators that are constructed according to Jordan-Wigner formula, where does the distinction
First, Majorana, as far as myself, Majorana fermions didn't appear until now, except this mentioned at the very beginning. But the idea is that we use in a little, we work in a little different basis where they are its own conjugates. Okay, so for this Majorana, but this will appear in a moment. But this is a name of the.
For example, the Jordan-Wigner transformation for Dirac and Majorana fermions.
But the name comes from the fact that in one case there are distinct particles and antiparticles, and in Majorana case particles are identical with antiparticles. And this does not seem to enter into this formalism in any way.
Here not, but there will be about Majorana in a moment.
But already there was a model called Kitaev model where that was important.
That's the Hamiltonian.
Yeah, but the physical model of Mr. Kitaev, he didn't know anything, I believe, about this all complicated mathematics. He just was constructing a physical model in which a quasi-particle in a real solid, right, in a particular solid and in particular states behaves as particles and antiparticles simultaneously. So that's why they call it the Majorana. It has nothing to do with Majorana, by the way. I mean,
From this point of view, these are rather spinless fermions.
yes.
Because there is no additional degree of freedom.
Absolutely. This is just a
As for Dirac,
kind of objects which satisfies anti-commutation relation for unknown reason.
The only quantum number is this
Is this the
level, single particle
the
level.
single particle level? Yeah. Precisely.
Moral change.
maybe to sum up, the Wei-Norman algorithm has, I think, it shouldn't be used for many particle systems, because the most efficient method to solve such problems is the Bogoliubov transformation. And it could be proven, for example, by comparing the computational cost of the direct Wei-Norman method and the Bogoliubov diagonalization. So the previously described method requires 2n squared minus n basis vectors. That means that it's necessary to calculate this number of commutators. So the total number of calculation steps is given by this expression.
But that goes as a quadrant of fourth power over.
Yes, that's why this one is better.
Yeah.
That's why Bogoliubov is better.
And of course,
But it says that the total number is larger.
yes,
The
yes,
Bogoliubov.
that's right. The Bogoliubov transformation requires only n
No, this
basic
is a
vectors.
quadratic function, this is a fourth power of n, so with increasing n, the SL tot must be larger than SB tot.
Yes.
Yes.
And
Yes.
but it's written differently, that the SB
But
tot.
look, there is a second part of this formula, because there is some equivalence symbol, which says exactly what you
If
say,
n is
that
smaller than
at
n.
some stage quadratic function wins
Yes.
over the quadratic function.
That's
So I would written that for n less n, that's correct, because it's well off.
Okay.
Okay, on which side you have the second part of equivalence
Well, I'm
is
reading
fairly relevant,
No,
no?
I'm reading from left to right, and
So
I
really,
stop reading
you need
on
to
something.
practice
No, but you shouldn't stop read on the left-hand side of the equivalence relation, because you will learn nothing, no?
Study Hebrew.
Okay,
That
okay.
means that if the number of modes is
This is equality we understand. We can proceed.
n more, this inequality means that if the number of particles equal 2 or more, Bogoliubov diagonalization is more efficient than Y homologous.
But if you have one particle, you don't have.
Yes.
You don't have a chain.
So it's always
Better to say that Bogoliubov always wins.
yeah.
No, that was my
And,
next question.
And some facts about Majorana fermions. Jordan-Wigner transformation for a Majorana operators. As one can see, the transformation is slightly different than for Dirac fermions. The only application of Majorana Hamiltonian that I found is the Kitaev model.
No. Then I can tell you that you should look at the volume stick like this, which you call on the topological insulators. And there is plenty of those, which are more or less.
But, okay, so the structure is more or less the same, or this which they use in graphene or something like that.
Yeah, it must be a particular geometrical structure
Yes.
of the substrate on which the particular points on the operators corresponding to the particular points on the spectrum of the Brillouin zone have this particular property, and that is what's called. And that's how the Majorana fermions have re-emerged in solid state physics.
However, the Kitaev model it is better to represent the operators as Majorana fermions than as Dirac fermions. Because in the case of Majorana fermions, the distinction between the red, like in this picture, and green.
This red and green, I understand, correspond to G1 and G2, yes.
Disappears. And also basis vectors defined for the Kitaev model form a Lie algebra. They are ordered this way and satisfy commutation close commutation relations. And this is the solution obtained using the Wei-Norman method. Maybe as it's difficult to notice, but the equation is simpler than obtained for Dirac-Fermats. And the second property of this equation is that it is predictable and has exactly the same form that does not depend on the number of particles.
So predictable, you mean that you can construct this exactly for the just repeating that you can construct it for the arbitrary numbers, yes?
Yes.
Number of Fermats.
And some properties of the solution, it also forms simple group that is not compact, not connected, and for some meshed initial conditions, the solution belongs to the, for example, orthogonal group or the spin group.
So what is finally the algorithm that has to be applied if one has this Hamiltonian with time-dependent coefficients? What are the successive steps in this program? I missed the
At first, I have to find all basis vectors. Then
we have the Hamiltonian, right? What are the basis? The basis vector are eigenstates of the Hamiltonian?
No.
No.
Basis vectors, for example.
No. Let's go back to the Hamiltonian. So we understand.
So this is the Hamiltonian.
This is the Hamiltonian, right?
Yes.
And psi is just the sum of creation annihilation operators.
Yes.
Now you can forget these are the operators.
No. Psi.
You don't need this, that they are sum of the.
They have some
The rest is
computation
built
relation.
up from psi's. The fact that the
Yes.
psi's are sum of i's
And the coefficients
are time dependent.
are time dependent.
Yes.
And now we want to find the evolution of the system in time. And that's the purpose. And then how do you proceed? What are the equations that must be solved in order to find the evolution?
No, but this equation you have written then exactly for the Majorana fermions you have written this equation and the less
I
transparent.
have to construct this matrix.
But what are the equations that must be solved? I understand that there are sets of differential equations.
Yes,
that
and
must be solved in order
and
to.
there are differential equations for these coefficients.
Yeah, but where? So the time derivative of g of.
Prime is time derivative here.
Yes, I understand, but you must invert the algorithm is you must invert the matrix A,
Yes.
and then C. You must find the coefficient C. The table-
No, coefficients C are the coefficients in Hamiltonian.
Yes.
These come from
The main problem is that
Yes,
this.
the solution of the Schrödinger equation is given by this formula, and it depends on the
Yes.
basis vectors and the coefficients G, and then I have to determine G from the coefficients.
The main problem is that this matrix A depends on G. So if you invert this, these are nonlinear equations.
Okay, so these are nonlinear equations.
Exactly.
Of course.
And these equations for Majorana fermions were written. She showed, I think, these equations.
The equations are exactly the same, but only basis vectors and the commutation relations between xi are different.
And the structure of this matrix A depends on the Lie algebra, on the underlying Lie algebra.
And on the next, here, wait. Here you next one, you had these equations and just
No.
for G1 and
Yes.
G2,
But if you look,
Oh yes.
Yes. Oh, these are
So
equations.
that's the basic formula. So
Yes,
one has to
yes.
solve these equations. Coefficients C come from the Hamiltonian,
Yes.
and
Exactly.
coefficients G are to be determined.
Mhm.
And that can be just put on a
But
computer
if you look at the previous slide,
and solve this.
even previous to
Okay. So
still one
this, the
back
basis of this algorithm is the set of nonlinear
equation. But if
Yes,
if
and
you just go-
ordinary nonlinear
if
differential
you
equations.
kind of
Exactly.
backwards
And
step,
the difference between the Dirac and Majorana system is that for Majorana system, if I order my basis vectors this way, I have always those equations, and they do not depend on the number of particles.
So as you maybe
This
remember,
results from the
I still don't see the difference between Dirac and Majorana, because you defined Majorana in terms of A plus A dagger.
yes.
So when you have the Majorana Hamiltonian, you can go back to A and A dagger just by inserting, instead of psi, A plus A dagger.
that's true.
So
But,
what is
but
true?
the difference that these particular combinations which enter into Majorana in this Hamiltonian-Majorana system close to smaller or
Of
to
course.
other Lie algebra.
Of
So
course,
it
because
could be
there are
simpler.
additional
Okay, so
equations.
Yeah, sure, there are
Expression,
exactly.
Okay.
So
can we
does it
move
correspond to the
backward?
story that Shimon
Backward, I mean,
told some months ago?
Yes.
to
Because
the
it's
definition
perfect,
of
it's
the
the end
still one backward.
group, and that's precisely
Okay, now, the question is that,
If we substitute,
the question is that this Majorana fairness, this Hamiltonian, appears only for a very particular lattice, which is drawn on the picture, right? And the time dependence of J1 and J2 means that this lattice changes. And then when it changes, when the angles become, how can the coupling change by the
Or the
changing-
strength of the coupling.
The J's are related to the lattice, and the dependence is not on the amplitude, which means that the lattice is squeezed or something, but also that the angles change. And once the angle change, then the whole geometry blows up, and there are no points, no special points.
That is true, but once again, if you try to simulate
So
this with some
in the physics, no, I mean, this is a Hamiltonian, and then you do all arbitrary mathematics, saying that J1 and J2 are arbitrary function of time. That's fine. But in the real physics, the time dependence of J1 and J2, if you want to still have the Majorana representation having anything to do with the real physics, is extremely restricted.
Łukasz, you are completely
yes,
right.
That's right. This is the main disadvantage of this method. It means that the basis vectors and their ordering.
Okay, but let's for a moment come back to physics of this. Okay, Łukasz, you are completely right that in this solid state models, that is exactly like what you say. On the other hand, I don't claim that it is possible. On the other hand, there are several methods of simulating, so it's quantum simulators method of simulating such systems with other means, okay? And then from time to time it happens that they can do more than it is possible to do in the solid state physics, okay? So this is, okay. I don't claim that it is in this particular.
Now I would.
But maybe let's
go to the next part of the presentation and give some facts about Jordan algebras. So they are power associative, satisfy Jordan identity, and there is a natural operation, Jordan multiplication, defined for them, and it has exactly the same form, so it's very similar to the definition of anticommutator for example, Fermat operators. Jordan algebras appear in physics. For example, they are connected with exceptional Lie groups. Also, they appear in string theories and algebraic formulation of quantum mechanics. Introduced by Jordan, Wigner.
This is the same Jordan. Karol asked which one. This is the same.
Kersher, and they are also useful in the in solving problems for symmetric spacing geometry and projection geometry. And there's the theorem that each simple Jordan algebra is isomorphic to one of these three families of Jordan algebras, that means symmetric of Hermitian matrices over real complex numbers or quaternions, or to Hermitian matrices over octonions, but only that means matrices 3 times 3. They form the so-called Albert algebra, and or to the spin factor algebra with this with such defined product. These algebras are called Euclidean, and they must be finite dimensional. Of course, the Jordan algebra is semi-simple. It could be decomposed into a direct sum of simple algebras.
What is this VW in the...
Scalar product.
V and W are
No,
treated.
on the right hand side.
Scalar product.
Oh, this is a scalar product.
Vectors and scalars.
Ta żarówka to powinien być to kółko. This sign of multiplication.
The circled cross is the circled point.
Yes.
Yes, and the definition on positive convex cone is a subset of vector space. This is closed under multiplication by the so-called convex transformations, where A and B are positive scalars. And this is the graphical representation of the convex cone. And there's for Euclidean Jordan algebras. It was proven a positive cone theorem. That means that one can identify the interior of the cone of a Jordan algebra with a manifold, and by diffeomorphism, and the algebra could be identified in tangent space, and then there is a well-defined exponential mapping acting on elements from algebra and transforming them into elements of the cone. And this is the analogy with Lie groups and Lie algebras. Because Lie group is, by definition, the manifold with a group structure, and Jordan and Lie algebra is defined as a tangent space. And then the Wei-Norman problem could be reformulated for Jordan algebras with respect to Jordan product. And this is a first order differential equation. It occurs, for example, in the Jordan quantum mechanics formulation. It's called the Jordan GNS model, when we have also the derivative of K. K is an element of the interior of the positive convex cone, X, I are basis vectors in the Jordan algebra, and also N is the linear superposition of basis vectors. This is the same problem, but with like on the first slide, but with respect not to a standard product, but to Jordan product. And the main question, is it possible to reformulate the Wei-Norman problem in such a way? In general, it's impossible, but if we choose the proper basis, yes it is. In general, there's a very simple algorithm to determine basis for Jordan algebras, especially for Euclidean Jordan algebras. One may always decompose any Jordan algebra into a direct sum of such sub-algebras. They are determined by so-called idempotent elements. An idempotent element is the element that, if it is square, if you have, for example, EI times EI is the algebraic multiplication, it gives EI. And if idempotent elements commute, they are called orthogonal. For Euclidean Jordan algebras, they belong to the family of algebras of Hermitian matrices over a field, for example, real complex numbers. Idempotent elements are simply the matrices with only one diagonal non-zero element. And this is the formula to determine the subalgebras.
Non-diagonal element rather than diagonal.
And those subalgebras are called diagonal, and those are called non-diagonal. And this decomposition allows us to determine basis vectors. For example, for the algebra of real symmetric matrices, and solve Wei-Norman equations for them. The problem, maybe I didn't mention it before, is that Jordan multiplication is not associated. So this problem is maybe it is easy to notice it, but this problem is not trivial, and in general it is quite difficult to determine these coefficients. But for this case, for example, the matrix of coefficients A is diagonal, and Wei-Norman equations are given by these expressions. And maybe to sum up, the Wei-Norman method is not perspective for Dirac-Fermat systems, and as it was very easy to notice, because it's less efficient and slower and has much bigger computational cost than, for example, Bogoliubov transformation. Majorana-Fermat systems are slightly better when it comes to apply the Wei-Norman method. And probably the most perspective problems are Jordan algebras system.
If they have any application to physics.
Yes. So this.
Now I have to defend
To
this.
physics,
Absolutely.
Yes.
There are lots of, I can imagine, in the problems of steering, where you have the
Exactly.
equations, linear programming in the, I mean.
Exactly. Lukasz, you are completely right, because this extends the method of solving equation of steer, of control, of steering. Exactly.
So I mean, so I think the last part, as far as I was concerned, was the only thing which physically has any sense to me. I'm sorry.
But not the Jordan reformulation of quantum.
No, yeah, sure. So but this is
let's
exactly.
face it, no mumbo jumbo can help us in understanding and doing better in quantum mechanics than we
Yes,
used
but
to.
that to steering and
The spirit.
control.
And now I have a question, which is, this is a way of solving explicitly. In some-
Yes.
It may be very difficult to
Yes.
calculate this coefficient, but that can be done by computer. right?
Exactly.
But for the homogeneous equation.
Now you want to learn from non-homogeneous.
I mean, if I had this equation
Mhm.
decay, right?
Yes.
Decay is empty, and n is constant, and I will add in homogeneous term the external force. Then I know how to solve it for constant
Yes,
f.
sir.
There is this integral, right? Which has a commutator sitting there. And theoretically, this commutator involves only k. So it is of the same kind of a.
This can.
The question is, of course, that, and then I have I don't know, I had a very quotation simple physical problem, which
Okay.
looks like this. Remember when our friend from Linköping was talking about the tippy top.
Okay.
The tippy top is the rigid body dynamics,
Yes.
which is, of course, dk is equal
Yes.
m. And then, of course, if the tippy top rotates, this matrix is time dependent.
Mhm.
So would that be?
This is everything is any model is here welcome.
I mean, I would look like
As you see-
whether this is whether that is possible to use this kind of a trick for looking for the solution of a tippy top equation.
As you see,
This last part is really remarkable. I think
the
this
second
is
part.
steering people,
Yes.
they are programming this. There are thousands of applications for this. I mean,
As you
so
as you
this is
saw,
I mean,
the
first thing
second
I
part.
forget about the Dirac and Majorana fermions. This is completely.
Yes. So let me.
No economist will ever dare to read it if you will write it.
Let us explain the project. As you saw, the last part was explicitly stated that it's in progress. So these are results which Katarzyna obtained in the last 1 month, maybe, or something like that. So this is really a working but it started simply from analyzing this fermionic problems. Okay, so. And then it evolved to that. Okay, so I will still try to think about this Majorana fermions because it's nicer as we saw, and maybe this, but definitely our aim was to apply this to kind of differential equations problem.
any more questions?
I have a question to this first part, because maybe the conclusion is not so bad as you show us. Because what about interacting systems, when this Bogolubov diagonalization cannot be done simply, but maybe your method can be applied to the non-quadratic Hamiltonians or not?
I tried to do it, but no.
No, this definitely does not close into closed Lie algebra. This is why the only I would say way is to introduce some small parameters and cut it on some Lie algebra, okay, and then compare it. But obviously it is there is no.
If there is a finite number of fermions, then of course.
Yes, that everything must close in GLN or something
No, but
like
for
that.
example, imagine that you have 4 fermions, but strongly interacting. for
Okay,
years, okay?
okay.
So then your Hilbert space is closed, and,
Whether this can be used to
but
solve
it
the
cannot
Hubbard
be
model.
solved by this.
I don't know about the Hubbard
Then you
model.
have
No,
everything inside like the unitary group on corresponding to the whole Hilbert space.
Okay, from time to time it can happen that it reduces to something small for particular choice of Hamiltonian, and that's maybe okay.
Because
but
for strongly interacting few body systems, this Bogomolov diagonalization.
No.
But
is
certainly-
not work.
Simply does not work.
But certainly the approach was to find some general, and now maybe looking for the models is a good idea. Okay, so
But in general, the dimension of the algebra generated by basis vectors do not depend only on the possible number of modes, but also on the
Computational
order of
complexity
Hamiltonian.
of these nonlinear equations
So, for
probably will
example, for
increase
interactive systems,
dramatically, so that
it would be
you wouldn't gain
it
anything.
would grow like
Łukasz, we know that it,
N4.
Łukasz, we know that it grows rapidly from this consideration which we did with Szymon Harzyński about the simple Lie algebras, that the complexity grows. Okay,
Yeah, so
to some extent this is not so trivial. Okay, so
no, it's not.
but that
I mean, I would rather think that this application, engineering applications
yes.
are more
We
important
completely
here.
agree. That's why Katarzyna insisted on including the second part, which is the problem.
A może to patentować?
Można patentować.
Okay, so if there are no more questions, thank you very much.
Może opatentujemy